B plus tree deletion. So this is our tree that has 3 levels. None of them are full. All these nodes, none of them are full. Let's try deleting 25 from this tree. Right, 25 is over here. If you want to find whether this 25 is available in this tree or not, you have to follow the path from starting from the root to the leaf node. Let's try locating 25 first. 25 may be in the tree or may not be in the tree, right? So let's see whether we have 25 or not. So you compare the 25, that's the value you want to delete, with the root. So root has only 15, so the 25 is greater than 15. So it should be, if it is available in the tree, it should be on the right hand subtree. So right subtree, you follow this right subtree of 15, you find 20, and then nothing else in this node, so you have only 20. So you follow greater than or equal subtree, that is the right subtree of this node, and then you locate the node and then scan through the node, and then you find 25 there. Now you want to delete this 25. So the node size, the node span, that is n, is 4 in this case, 4 pointers and 3 keys. So if you delete 25 from this, so n divided by 2 ceiling is the minimum number of keys this should have. N divided by 2 ceiling. N is 4, divided by 2 is 2. So the at least 2 nodes. You must have at least 2 nodes in a given node to be considered as not underfull. But in this case, if you delete 25, this becomes only 1 key, that is less than 2. Minimum number of keys that is needed there. So this is underflow. Obviously, now you need to follow a merging mechanism to restructure this tree so that it follows all the properties of B plus tree. Right. What you do is, if you find any node that is underflow, you need to find the sibling of that node, right? So the sibling of this node can be on the left hand side or on the right hand side, either side of this one. If there is another node from this pointer somewhere here, that becomes another sibling, because those nodes are sharing this common parent. This is not a sibling of this, because that is in a different subtree. It's not sharing common immediate parent. Now if you delete 25, this is underflow obviously. Now you want to find the sibling, that is the only sibling, this is the only sibling that this node has. Now you want to merge this one onto this, right? Now there are 2 possibilities. One is your sibling is full, or your sibling has some space. If your sibling is full, there are 2 things happen. So you have to merge with the sibling, and then that sibling becomes overflow, and then you have to split it. But in this case, sibling is not overfull or full, it has some space, empty slots. What you do is you copy over this 20 to this empty slot. Okay, let's see what happens next once you do that. Now once you copy over this 20 to here, there is no node pointed by this pointer. Now what will happen is your parent, that is an internal node, becomes underflow. Okay, now it is underflow. When some internal node underflows, it has to find its neighbor so that it can merge into. Now the neighbor for this node is this, that is 6 and 10. Now there are two possibilities. One is your neighbor is full also, but in this case it is not. If it is full, when you merge it, you have to split that node as well. But in this case, you need to copy over 20 to this empty slot when you merge. There is a special thing happening here. When you want to merge two internal nodes, you do not simply copy over the value to the other one. So this is the thing. You need to consider the parent value key that is separating these two internal nodes. What is that? That is 15. 15 is separating this node and this node. So when you want to merge the set of values from this node to this, what we do is you replace the leftmost element of this node that we need to merge into the other one, the leftmost node value, that is 20 in this case, that is the only value, but it can have many other values if the number n is very large. But in this case it is only 20. When you merge all these values here, what you do is you pull this value down and then replace that one with, replace the value of the first, that's the leftmost element with the root value. So that is 15, right? So when you merge it, you pull down the root value and then replace the leftmost element of this merging node. And then something special happens there. So this one shows you need to merge these two and then pull down the key that separates these two nodes, right? That is 15. Once you do that, this subtree is following the B plus tree conventions, right? So these values are greater than or equal 15. This value is less than or equal 15. Less than 15, sorry. Now, once you do that, when you merge, this node is disappearing, causing this node to be underfull. Now, this is invalid, and that is the root. If a particular root has only one child, as in this case, what we do is we delete that root and then make the immediate child as the new root of that tree, causing the tree to reduce its height. Now, once you delete that 25, that is propagating upward and then again upward until it hits the root, and then root becomes underfull, and then we delete that root as well. Now this is the resulting tree after you delete 25 from this tree. To recap, if you delete this 25, this becomes underfull. Then you need to find a sibling that you can merge this node with. In this case, there can be two situations. One is that sibling, both siblings, if there are two, are full, right? In that case, you need to merge and split. But in this case, we have some space, so we copy over that 20 here. We move that 20 here, causing this root to become underfull because one pointer is now null because we deleted this one. If this is underfull, then now we need to merge internal nodes as well. When you merge two internal nodes, what happens is you need to pull down the separating parent key, that is 15, right? When you move this one over here, you replace the leftmost element of this merging node with the value available in the parent, that is 15. So you move the 15 here, causing the root to be underfull. Now if the root is underfull, what we do is we delete that root and then make the immediate child as the new root, resulting this tree. Now there is a different scenario here. So again the same tree, but with some little bit more items here, right? So for example, this one has 12 and 13 compared to the previous example, right? So this tree is full, this tree node, leaf node is full, and this internal node is full. Now let's see, we want to delete 25, right? So if you want to delete 25, what will happen? So this node becomes underfull. So in that case, you need to merge this one with the sibling. In this case, this is the only sibling that we have. But the issue with this one is that sibling is full. So this sibling is full. So what we need to do is we need to merge this one. At the same time, we need to split, right? So if you merge this node with the remaining value of the other node, so this becomes 15, 16, 17 and 20, right? You copy over that one to a temporary location and then split in the point where it is pointing n divided by 2, right? That is 2. You get 15 and 16. So let me copy this over. So this is my new node, and then 17 is removed from this one because we get another node here, and this one becomes 17 because of the split, and this one is 20. Now when you split a leaf level node, what you do is you get the leftmost element of the new node and then copy that one over to the parent and rearrange these node pointers so that it is pointing to our new structure, and delete these two. Now this is our new tree. It is not propagating to the top. Okay, now it is not propagating to the top. Now suppose that you want to delete, again you want to delete 20. Now there's a different scenario. Now this effect is propagating to the root as well. Let's see what will happen. If you want to delete 20 from this node becomes underfull. Okay, underfull. Now you want to merge this underfull node with the sibling. Now you will need to look for the sibling. There is only one sibling because there is no any other sibling on the right hand side. So you check the sibling. Sibling has space, right? What you do is you copy over that 17 here and then get rid of this node. Now what will happen is this node is null now, pointing to nothing, causing this parent to be underfull. Now you cannot stop here because this tree is not valid now. What you need to do is you need to merge this underfull node with the sibling. This is the only sibling. Now there is another situation, a brand new situation, that the sibling, that is an internal node, is full. what you do is you merge these two. When you want to merge internal nodes, what you do is, as we did in the previous example, when you merge these two, the key value separating these two nodes, you pull it down and then replace this first leftmost element of the new node that we want to merge into the other one, right? So in that case, this is 15. This becomes 15 and 15 comes over here, and then 6, 10 remains here. So this becomes 12 and 15. And this 12 is gone because it is suppling with that. So this 15 was pulling down, replacing that one. And instead of keeping or copying over this value over here, what we do is we move the leftmost element of the new node to the top, that is 12. So this one is only 15 and then nothing else there. Now if you rearrange these nodes, so this is what happens. Now you want to delete 20 from this. Okay, so I'm repeating the thing. So if you delete 20, you simply get rid of this value, and now this becomes underflow. You need to find the sibling to merge with, and then that is the only sibling, and then that sibling has some space. What we do is we copy over that 17 over here and get rid of this node completely. Now the problem with this one is root node becomes underflow. Now we need to find the sibling to merge this one with. Now these are internal nodes. The way we merge internal nodes is slightly different. Now you need to merge this one with this. When you merge internal nodes, what you do is you pull down the separating parent key value and replace the leftmost element of the merging node, right? That is this. Make it 15. Okay. Now when you merge 15 here, so this is overfull. What you do is you need to split this four key value node, right? So that becomes 6, 10 becomes 1, and then 12, 15 becomes another one. When you split internal node, instead of copying over the leftmost element to the parent, what we do is we move that over to the parent. So it should be like 6, 10 and 12, 15, but it is not like that way. It is 6, 10, 12, 15 comes here as a new node, and then rather than keeping 12, 15 in the new node, what we do is we push the 12 to the parent. And after that you rearrange this node pointers. Like this. All right. So in summary, when you merge leaf nodes, so the parent becomes underflow. In that case, you have to merge the parent as well. But if you split leaf node, what you do is you divide the node into 2 based on the formula n divided by 2cl, and then copy over the leftmost element key value of the new node to the parent. But when you merge internal nodes, you need to pull down the key value that separates these two merging nodes, and then replace that one with the leftmost element of right hand side node. When you want to split an internal node, what you do is you create the temporary node that has one key value more than it can accommodate, and then you divide this one into 2, and then already existing node, there is no change for that, but the newly created node has now 2 key values, and what you do is you push the leftmost key value of the new internal node to the parent. So that's what happened here, right? So when you merge these two, it has to be 10, 6, 10, 12 and 15, and then if you split that one into 2, it becomes 6, 10 and 12, 15. But because this is an internal node, what we do is we push the leftmost node of the new node and then push it to the parent. That's simple. That's it.